All right, we're back. So you should have been able to find a video that walks you through how resampling stats works, and then a real short video kind of on the history of William Seeley Gossett, also known as student, and then a chalk talk about t-test calculations and degrees of freedom. So next we're going to compare our calculated t-value from that last chalk talk video to a table of t-values. So what does the t-distribution look like? Here you can see t, which is a pretty normal looking, a little squished maybe, distribution. And you can see how the distribution changes as the degrees of freedom change from 1 to 2 to 5 to infinity. So basically the t-distribution varies, roughly between -4 and +4. And you can calculate values of t much larger than that from your real data. And when you have a really big t values, that generally means that you have a significant difference between your two means. So how do we know exactly what your p-value is? You use a table. So this is one way to do it. So statistics books used to have just tables and tables of values in the back. And so you would take your calculated value with t and 8 degrees of freedom to the table, and you would go, you'd be able to go down this, this row here, gives you the degrees of freedom, v degrees of freedom. And so we know for our example, our t had 8 degrees of freedom, and our calculated value was -3.21. So these are all in the positive, but basically we're looking for values larger than 3.21. And what we can see is that at an alpha of 0.05, our calculated, or our critical t-value, our critical t-value would be 1.86. So right here, so you go degrees of freedom 8 and an alpha of 0.05. As long as our t-value is greater than 1.86, then we can reject the null hypothesis. Oops. So this is what we call the critical value of t. And since our value is bigger than that, we can reject the null hypothesis. Now, technically, our value of t is bigger. And so we could go all the way over to here because our value of 3.2 is somewhere in between 2.896 and 3.35. That actually tells us that our p-value associated with the t-value of 3.21 is less than 0.01. So we would report p less than 0.01. So what is this p-value thing? P-values are basically a guide to whether you're going to reject the null hypothesis or accept it. And so it's like a yes-no. That's all it really is. So if it's less than 0.05, then you can reject the null hypothesis. Our null hypothesis was that the mean number of ant mounds in forests would equal the mean number of ant mounds in the field. And so at a p-value of less than 0.01, we can reject the null hypothesis. They are not equal. Okay, the means are not equal. And we could say, after looking at the data and noticing that there are more ant mounds on average in the field, we could say there are significantly more ant mounds in fields compared to forests. And then we would put our statistics in parentheses as evidence to support that claim. That's where statistics belong. They don't belong as nouns in your sentences. So you would say this statement, there's significantly more ant mounds in fields compared to forests, and we would say the evidence in parentheses is a t with 8 degrees of freedom is -3.21 and a p less than 0.01. Okay, so p-values are part of the evidence from the statistical test. A p-value measures the probability that observed or more extreme values would be found if the null hypothesis were true. Okay, so that's a little bit tricky to understand. A p-value is also a probability that you're making what's called a type 1 error, when you're accidentally rejecting the null hypothesis when it's actually true. So type 1 and type 2 errors, I'm just going to take a minute to explain them. And it's important to understand that in reality, whether we can know this or not, the null hypothesis is either true or false. Okay, so there's reality, there's truth out there. Now our job is to find it, right? So if we were all knowing and had complete information, we would just know whether there were more ant mounds in the field or in the forest. And we wouldn't need statistics, but we're not all knowing. So this table shows you, in reality over here, the null is either true or it's false, okay? But we don't know which it is. And so we run our tests and we do our work, and maybe we accept the null. Now, if we accept the null and it's true, then we're correct. We've made the right choice. Or if we reject the null and the null is actually false, then we're also correct. So that's what we're hoping for. We want to be in one of these two boxes. Now, if we reject the null, but it's actually true, we're making a type 1 error, okay? If we accept the null, but it's actually false, then we're making a type 2 error. And we want to minimize both the type 1 error and the type 2 error if we can, but we can't minimize them both at the same time. So I'm going to talk to you a little bit more about these two types of errors. So type 1 error, alpha, is basically false positive. So say we do a study and we report that a pollutant causes health problems when it actually doesn't, or say you go to the doctor and they tell you you have cancer, but you actually don't, right? So those are bad things, okay? That's a little different. A type 2 error, beta, is a false negative. In this case, they test you for cancer, you test negative, but you actually have it. So there's some differences in terms of different types of sciences. In ecology, we try to minimize type 1 errors. And in medicine, they try to minimize type 2 errors. So you cannot minimize both alpha and beta at the same time. We would rather be wrong in the way that, there is an effect, but we don't see it, than to basically say there is an effect when there isn't one as ecologists. And doctors would rather tell you that you are sick and treat you as if you are than to let you be sick and not know about it and not get treated. Okay, so there's some differences between science.